So let's investigate what these wave functions would look like in the two different cases. So in a case 1 type scenario, I can make a plot of phi versus x, and here I'll sketch in my two locations, right? This location here is minus a, and this location here then is plus a. And what I see in the type 1 case, right, is in both cases, of course, I've got my growing exponential here in region 1. Then in region 3, for x greater than a, what I have for the type 1 case is just the decaying exponential. And then in between, I have a cosine function, which attaches perfectly at the boundaries. So the simplest cosine function is just like cosine of kx. So the cosine function, you remember, starts at the origin with 0 slope and then curves downward like so. And then on the other side, I'd have the same thing. A little bit wiggly, my line, but I think you see how that solution would appear. That's very nice. A real cosine would be a little more rounded at the top, but I think you get the idea. Now, as I go up in energy, I could have a different value for k, so there would be more of these oscillations. Oh, notice, by the way, this function I just drew has no nodes, right? So that is very clearly goes with the ground state energy, E0. The next cosine might come up like so. It would cross this axis. And if it's the next of these states, it should be the second state should have two nodes, and in fact, cosine can do that for me. It'll go negative here and come up like so. Very good. And that, again, that has two nodes, so that's very clearly E sub 2. And then the next type of cosine could have yet another oscillation. That's a little harder to draw, but it might come down, right? It has to come up here and then down and then back up and attach like so. And if I count the nodes on this one, there are 1, 2, 3, 4 nodes. So you see, I always end up with an even number of nodes because I am at, I'm using the cosine function, which is an even function. And that's why I'm always getting the even numbers being this particular type of solution. So what I'd like you to notice that what these functions here all have in common is these are all symmetric, or sometimes what are called even functions. Very interesting. And by even, we mean they have the mathematical property that f of x, well, in this case, it's the wave function. But in general, an even function is that if I flip the sign on x, all I get back is the same function again. So that's type 1. The type 2 solutions, I will sketch those. They're very similar, but a little bit different, of course. Right? So the type 2 solutions go from minus a to a. In the first region, again, I always have this growing exponential piece that we have to attach to. But now for type 2, when I go to the far right, notice it's minus of that decaying exponential. So it actually looks something like this. So it's not a symmetric function, but it's kind of the opposite over here. Now, in between, I have to put sine functions, and sine functions have to cross the origin with some amount of slope. And if I'm going to make this, it's a minus sine function, so it should have a downward slope. And if it's going to attach to these two, then it appears I should have maybe something, whoop, that didn't come out so nicely, something more like so. Right. That would be the first of these, and you can see it indeed has one node, so this is clearly an E1, right? This would go with the first state, above the ground state. Now for sine, I can do the same thing as before. I can cross the axis a number of times, but because it's a sine, I always have to cross the axis also at the origin. So I might be able to come up and down here, cross the origin, up, and then I've got to cross the origin and attach like so. And this state would have 1, 2, 3 nodes. Good, so that would be E3. And you can continue in the same way. So the even functions give me E0, E2, E4. So those definitely make sense for the type 1. And then for the type 2, these are a different type of functions. These are also symmetric functions, but they're not completely symmetric, right? These have the property that if I look at f of minus x, if I flip my function around, putting this side of the function over here on the other side of the x-axis, what happens is the function itself gets turned upside down. So f of minus x equals minus f of x. These are typically called odd functions. It's a different type of symmetry that we have. So they're symmetric still, or sometimes this is called antisymmetric. They're symmetric, but what seems to have happened is my system has factorized into two very different types of states, either even functions or odd functions. And the origin of that, it would appear to be, has something to do with my original potential, right? My original potential was completely symmetric with respect to x. If it weren't symmetric with respect to x, there'd be no particular reason to expect the tails on either side, for example, to be the same, and I wouldn't have any particular type of symmetry. But when I have a symmetric potential, what seems to happen is my solutions factor in a way that reflect that symmetry. But it's not as simple as that I simply get even functions back again that are symmetric. I can also get these antisymmetric so-called odd functions. So this then leads into an interesting segue for us to begin to consider in general the effects of symmetry in quantum mechanical systems.